All right, we should probably get started. So the last time we were talking about these, how to pick between various query plans, right? So there was this dynamic programming algorithm that allowed you to come up with an estimate for a logical query plan, and before that we had thought about how to for every single operator, how to pick between various physical implementations of that operator. So for hash join, we considered various variants of hash join. For joins, we consider various variants of joins, including hash joins. For hash joins, there were many variants of hash joins, and then there were nested loop joins, sort merge joins, and a whole bunch of other variants that we talked about. So there is this gap in some sense because we've talked about wanting to use the logical plan which specifies the order in which these operators are executed. But for each operator, we do need to pick what physical implementation we're going to use. And so that's this gap between our earlier part on query execution and our current part on query optimization. So I covered a little bit of this last time, so I'll recap that and then go ahead. Right? So from this dynamic programming stuff, the next step is to compute the physical query plan once you've decided on the best possible logical query plan using dynamic programming. And so essentially what we want to do is for every operator you need to figure out what the memory is, or whether any of the input operands are sorted, and all of these considerations can help pick between various physical implementations for each operator, right? So for instance, if you have a lot of memory, then you can possibly use an operator or an implementation of an operator that caches, for instance, one of the relations in memory, right? And if one of the input operands are sorted, then you can use a more efficient query execution strategy for that particular operator. And beyond figuring out how to implement each operator, the second step that we need to figure out is for every intermediate result, should we materialize it? So should we create the result entirely and store it on disk, or should we pipeline it? So basically, are we simply generating the results one by one and then passing it to the next operator without materializing it, without storing it on disk? Okay, so these are the two alternatives that we have for each intermediate step in your query plan, and for each for each operator we have various choices, right? So this is the decision for operators, and this is between operators. Okay, so these are the two things that we need to think about and pick once we've decided what a logical query plan looks like. And a logical query plan will probably look something like this. It's a tree essentially, and basically what you need to do is for every step, either reading the base relations or reading the intermediate relations, you need to decide which algorithm to use, and between steps you need to decide whether to materialize or whether to pipeline, right? Okay, so let's go to one example that I talked about in the previous class. And like I mentioned in the previous class, we're going to be talking about the actual costs now that we've selected the best possible logical query plan. The next step is going to be on actual costs for each operator as opposed to cost of intermediates. Okay, so we're going to switch back to talking about that because we're switching back to physical implementations. So we talked about this particular logical query plan, which was a left deep join, plus the algorithm that was used was essentially 3 executions of a hash join with materialization in between. Okay, so essentially the way to think about this is for S you create a hash table, you use R to probe this hash table, you generate the results, okay, and then you write out the results to disk, and then you read these results back to disk, back to memory. In the meanwhile, you would have created a hash table with T. You probe this hash table with tuples of this intermediate result. You write out the results to disk, right? Write out the results of the join to disk. Once again, read them back in. In the meanwhile, you would have computed a hash table for you in memory. You probe this hash table, any output you write out either to disk or you provide to the user. Okay, so once again, the strategy was you created a hash table for S, you read in all of R, you do the join, you write it out. So that is V1. And then you create a hash table on T, you read in all of V1, you do the join and then you write it out as V2. Create a hash table on U, read in V2, and then one block at a time, and then do the join and then write it out, right? So the final result is going to be R join with S, join with T, join with U. V1 is basically R join with S. V2 is R join with S, join with T, right? So that's this query execution strategy. So basically what we had to decide was, look, for this particular join and this join and this join, we are using hashing, right, where we are constructing a hash table on one of the two relations and then reading in the other relation. The second thing is, at the end, between steps here, this step and this step, we are writing out the results to disk, right? So we are materializing. So in this case, we are materializing the result. In this case, we are materializing the result. Okay, so what would the cost be for this? So these are the decisions that we had to make for this logical query plan. And the cost was, you read in S, read in R, both of them you read in only once. You write out V1, so this is the first join. And then you read in T, read in V1, write out V2, so your second join. Then read in U, read in V2. And the final writing out we are not going to count, so this is the third join essentially. Okay, so these are the three steps. And therefore the cost is B of R plus B of S plus B of T plus B of U plus 2 times B of R join S. V1 is R join S. And then 2 times B of R join with S join with T. This is V2. Okay? And here the cost of computing intermediates was simply 2 times B of R join with S and 2 times B of R join with S join with T. Why did this 2 come up? Well, the first step is you're writing it out to disk and then you're reading it back into memory. And because of that, you have this appearing twice. How much main memory do we need? The main memory is a maximum of the number of blocks in S, T, and U. So why is that? Well, you need to construct a hash table of S and a hash table of T and a hash table of U at some point during the query execution. Therefore, you need as much main memory as is required to store these hash tables. Okay, so that's essentially this particular physical implementation of this logical query plan. Okay, any questions about this? Is this perfectly clear? Yeah? Okay. All right. So the next approach, if we had more memory, is a fairly straightforward approach where we are just going to pipeline. We are not going to materialize anything. We are just going to pipeline through all of the operators. And so what we are going to start by doing is to create a hash table on S, create a hash table on T, create a hash table on U. And then we'll start with a tuple of R, probe S, okay? And then compute the join of that tuple with S, and then we'll send it to the next operator. We're not going to materialize it. We'll just send it to the next operator. The next operator is going to use this new joined tuples to probe T, okay, which is a hash table on T. Once again, the result is going to be directly pipelined to the next operator. You're not going to store it on disk. And this is going to be looked up into U. And then finally, the final joined tuples will be returned to the user or written out. So once again, so you are creating 3 hash tables, one on S, one on T, one on U. And then you are reading in the tuple corresponding to R, or blocks of tuples corresponding to R. You are joining these tuples first with the first hash table on S, so once you've joined it, you have the result tuple, let's say, is Y. You take that tuple Y and then you join it with hash table 2, which is on T, and then you get the result tuple, which is Z. You take that tuple and then you join it with hash table 3, which is on U. Your final result tuple is U, small u, and then you write that out to the output. Okay, so here you are essentially skipping the step of storing the intermediate relations R joined with S or R joined with S joined with T. You're simply pipelining through the whole process. And therefore, the actual total cost of this plan is basically you're reading in R once, you're reading in S once, you're reading in T once, you're reading in U once, right? The other thing is that in the middle, you're not doing anything in terms of I/O, right? You're basically pipelining through all of those steps. You're not writing anything to disk. You're not reading anything from disk. And therefore, the cost of these intermediate steps is just one big zero. So basically, your cost is just reading in all of these input relations. Okay? So the total cost is this. The cost of intermediates is 0. And how much main memory do we need? Well, notice here that you had to have hash tables on S, T, and U in memory at all times. And because of that, the amount of memory that we need is B of S plus B of T plus B of U. So these are two extremes, right? So one extreme is after every operator, I'm going to materialize. This is, I'm not going to materialize the result of any operator. And then you can imagine schemes in the middle where you materialize after some of the operators but not the others, right? For example, you could, let me erase some of this. You could, for instance, say, hey, I'm going to do these two in a pipeline manner, then I'm going to materialize here and then do this join. Okay? Makes sense? So if I were to do that, what would my costs be? Let's work through that. So if I were to do a pipeline join of both of these and then do a materialization step here and then do this join, what is my cost going to be? What are my memory requirements going to be? What do we think? You can tell me the answer for pieces first. So you can tell me the cost and the memory requirements for this piece or this piece or the stuff in the middle. What do we think? Yep.
So you said for the bottom part you're going to pipeline and the top you're not?
Yes.
So then I think the cost would be obviously B of R plus B of S plus B of T plus B of U, and then plus B of R join S join T.
You're close. So, so like you said, the first part is absolutely right. So B of R plus B of S plus B of T plus B of U. And because I'm pipelining, I'm not writing out the intermediate results here.
Yeah.
So you're not writing out the intermediate results here. So he was right in saying that this doesn't feature into the costs. And then he said B of R joined with S joined with T. But it's not just one of this. It should be two of this because you're writing it out once and then you're reading it back in from disk. And therefore, the cost of intermediates here is 2 of B of R joined with S joined with T. And that's the only intermediates cost. Okay, because this intermediate, there is no cost because you're pipelining through that. Okay, now let's talk about the memory requirements for this. What are the memory requirements? So once again, I'm trying to try to erase some of this. I'm trying to pipeline through this much and then do this step after materialization. So what are my memory requirements. Yes?
Max of either RST,
Max of,
BFR, BFS, BFT, plus all the
wait, so max of BFR plus BFS,
plus BFT, or BFR join S
or BFR join S join T. Okay, so what is the rationale behind this?
So while pipelining, you're either keeping all of the lower or the upper one together. So it should be either all of these would be in the memory at the same time, or the upper pipeline or non-pipeline part would be there.
So I think instead of thinking of, okay, so this is not quite correct, and let me try to explain why. So the way to think about this is, what do you need to keep depending on the algorithm that you're using, right? So here you're using hashing, right? So in this case, I'm saying I'm going to take this relation R, I'm going to construct hash tables on S and T, and then I'm going to pipeline through these tuples. In order for me to be able to do that, okay, up until this point where I'm materializing, I need the hash table of S and T to both be in memory, right? So for that, I need to have BFS plus BFT to be, I need to have that much memory, okay? Now that I'm done with that, I'm going to write out the results to disk, and because I'm writing out the results to disk, you can effectively imagine that this didn't even happen, right? You can just forget about it. It's just done because you've written out the results to disk. Okay, so the next step can essentially proceed as if you're starting afresh and doing a new join between two relations. Now, for that, you've once again decided, in this case at least, to do a hash table on U. So because you've decided to do a hash table on U and you want a one-pass hash join, you need to store all of U in memory, and therefore you need to have B of U to be another potential thing that you want to be less than M. So basically, max of these two things needs to be less than M. Okay, so this isn't quite correct. Max of one of these two things should be less than M. Okay, so does this make sense? Okay, all right. So let's move on to a slightly more complex example. And here there are many different alternatives, and I want to walk you through some of them. This is a fairly complex example, okay? So just, I mean, if you don't follow completely in class, go back and stare at it. And this is just an indication for how complex query optimization can actually get. Okay, so what we've decided so far is we've decided to do this logical query plan to join between R, S, and U. Okay, so it's a left deep join. R has 5,000 blocks, S has 10,000 blocks, and U has 10,000 blocks. Okay, and K is the number of blocks for R join with S. Okay, all right. And let's say my main memory buffers is 101 buffers. Okay, so this is my main memory requirements. So let's start with the simplest possible thing I can do. If I didn't want to worry about memory at all, what would I want to do? Well, I would do a two-pass hash join. Right? A two-pass hash join essentially allows me to not worry about memory requirements as much, because memory requirements there are, it's basically a quadratic requirement. So I need RFS or BFR or BFS to be less than the square of the memory, right? So it's a pretty relaxed memory requirement. So the simplest thing that I'm going to try is I'm going to use two-pass hash joins for this join as well as this join, and I'm going to materialize between them. Okay, so for two-pass hash joins, what would my cost be? Well, if you remember two-pass hash joins, I needed 3 times the cost of each relation as the cost of the two-pass hash join. Okay, so essentially you are you're not able to store any of the two relations in memory at once, and therefore you're going to hash things and write them out once, hash things, write them, hash and write out the first relation, hash and write out the second relation, and then read them back in, and then do the join. So essentially, the two-pass hash joins, if you remember the query execution lectures, was 3 times BFR plus BFS. Okay, so that was the cost of two-pass hash join. And then let's skip this materialization step for now. Let's assume that you've taken the result of R join with S and written it out to disk. The next step is 3 times of K. K is R join with S and B of U. So this is the second hash join, this is the first hash join, and so far so good. And the last one is, so far we've not accounted for the cost of writing out the first output, so which is R join with S. For that I have an additional cost of K. Okay, so this is the cost of the first join, this is the cost of writing the output out, this is the cost of the second join. Okay, so this overall evaluates to 75,000 plus 4K. Okay, any questions about this? Yes?
Could you say one more time where the 3's came from?
So this is the cost of the hash join that we, the partitioned hash join that we considered during the query evaluation portion. So basically you bring in R, right, and then you hash on into buckets, and then write them out. Bring in S, hash into buckets, write it out. And then you need to ensure that one of the two buckets of R and S can fit into memory. So let's say maybe the bucket of R fits into memory, and then you pipe through that corresponding bucket. In S, you pipe through the blocks one at a time. Either way, it's you read in relation R, read in relation S, write out relation R, relation S in a partition fashion, read in relation R, relation S once more time. Then the final output, you're not counting that cost. But overall, it's read in, write out, read in again, so 3 times each relation. Right? Any other questions? Okay, so this was the simplest case. We didn't really have a stringent memory requirement for this. Let's look at that memory requirement before I go ahead. So the memory requirement was essentially something like minimum of BFR and BFS must be less than or equal to M squared for the first join, and minimum of K and B of U must be less than or equal to M squared for the second join. Okay, so that was the memory requirement. Let's look at a slightly more smarter plan. Okay, so a slightly smarter plan would essentially do the same hash join in the first step. So partition hash join in the first step, but we're going to be slightly smarter about what we do with the output. Okay, so we are going to hash R on X, which is the join attribute, into 100 buckets. Remember that we have, yes, so we have 5,000 blocks of R. If you have 100 buckets, you have 50 blocks per bucket, and then you're writing that out to disk. So that's step 1, hash S on X into 100 buckets. Each of those buckets have 100 blocks because you have 10,000 blocks in S. Once again, you're writing out into disk. These are just the steps of the partition hash join. And then I've decided, since R is a smaller relation, so I'm going to read the buckets of Ri, the buckets Ri of R into memory, and then join with one block of S at a time. So I have 50 buffers for holding all of the blocks of each bucket in memory. I have one buffer for storing one block of S at a time, and then the result is going to be hashed into 50 buckets. Okay, so I have remaining 50 buckets. So I had 101 buckets to start off with. 50 buckets are used for storing one bucket of R. 50 blocks are used to store one bucket of R. one block is used for storing one block is used for storing one block of that particular bucket of S, and then the remaining 50 buffers are used for the output. Okay, and I'm going to hash the result on Y as a precursor to the next join. Okay, so I'm going to hash the result on Y into one of these 50 buckets. Okay, is that clear? So I have basically the first two steps should remind you of partition hash join. All that I'm doing is breaking it up into buckets. Okay, nothing surprising those two steps. The next step is the interesting one. So I'm reading in, so I have 101 buckets. Okay, so let's say this is 50, this is 50, and this is 1. Okay, so I'm reading in all of the blocks of one bucket from R, so let's call that Ri. Okay, and I'm reading in one block at a time from bucket Si. Okay, and if I cycle through all of the blocks of the bucket corresponding to Si, then I can compute the join between bucket Ri and bucket Si. And if I do this for all I, then I'm done with the hash join, right? That's essentially the idea behind the hash join. Yes?
So like remaining 50 is like R join S then?
Remaining 50 is what is used to store the R join S. Yeah. So I'm essentially doing the join between R and S and then hashing the result and storing it. So it's using a hash function on Y. I'm doing this so that I can do the join with U next. Okay, so and remember that the join with U is on Y, so I'm going to use that carefully. Okay, so I'm going to take the join tuple, hash it on Y, and store it in the remaining 50 buffers. Okay, so far the cost is 3 times B of R plus 3 times B of S. Why? Because the cost of this is B of R, cost of this is B of S, and the cost of this is actually 2 times B of R, 2 times B of S, because you're reading in and then writing out, right? So it's twice, reading in and writing out, so twice, and for this it's B of R plus B of S. Okay, so the cost so far, which is the same as the cost of the two-pass partition hash join, is 3 times B of R plus B of S. Okay? All right, so the next step is what is interesting. So if K, the joined result, is less than 50 blocks, so whatever we had allocated for it, so remember that we had 101 blocks, and we had bucket of, okay. So this was storing one bucket of R. This was storing one block of a bucket of S. And so this was 50, this was 50, this was 1. And this was a hash table on Y of the result, right? R joined with S. So if the number of tuples or number of blocks of R joined with S, B of R joined with S, is less than or equal to 50, then you can store the entirety of R joined with S within these 50 blocks. Correct? So if the size of R joined with S, which is K blocks, is less than or equal to 50, so less than or equal to this much, then you can store the entire result of the join within memory. So you compute the join between R and S and you store it in this hash table. If it fits within 50 blocks, then you can just keep it there. Okay, you don't need to spill to disk. So the next step then becomes easier. So if K is less than or equal to 50, you keep all 50 buckets in memory, and then you read U from disk, one or more blocks at a time. It's entirely up to you. You then hash those blocks into the same hash table. So the second step, let me draw another diagram for the second step. So for the second step, this hash table on R join with S will stay as is. You have 51 other slots that you can use for bringing in U. Let's say you just use one of those blocks. So you bring in one block of U at a time. You once again look into this hash table. You find tuples that join. You write it out to an output block. And then these output blocks get written out to disk. So overall, if k is less than or equal to 50, you can essentially keep all of the buckets in memory, and then you can basically read U one at a time, do the hashing, and then do the join, and then output it. Okay, so essentially you're not writing out R join with S. You're essentially skipping that step. So the cost here is basically the cost of the first step, the 2-pass partition hash join, and the cost of reading in the blocks of U. That's it. Okay, so there's no other cost. Is this clear? Yeah.
So for the, like, since you're storing R join S in those 50 blocks, then the 51 blocks are used for, like, U, and then the results of R join S join U.
Yes. So you can, I mean, essentially you only need 2 blocks for that. You can bring in one block of U at a time, and then one block for the output. That's all you need. So you don't really need all of the 51 blocks. But you can bring in more at a time if you like. It doesn't matter. The cost will stay the same. Anyone else with questions about this? Okay, so what happens when k is greater than 50, right? So what happens when you can't store the intermediate result of R join with S in memory? Then this won't work, right? Because you can't, you have only 50 blocks that you can reserve for storing the results of R join with S. If it goes beyond that, then you have to materialize. You have to store something into disk. But once again, you can be smart about this, and let's talk about how you can be smart about this. Okay, so essentially you have only 50 blocks for the results of the join, so the intermediate results can't be stored in memory. So the next approach is to essentially say, I am going to hash the so I have, once again, I have 50 blocks for R, 1 block for S, and then 50 blocks remaining. Okay, so far so good. So this is what I have for storing the results of R join with S. Now, what I'm going to do is, as I'm computing the join of R join with S, I'm going to hash this in using Y into a hash table here, essentially partitioning the domain of Y, or partitioning the set of tuples in R join with S into 50 partitions. Okay, so once again, I'm going to use the hash table and partition it into 50 partitions. So essentially, I have k is the number of blocks of R join with S. I'm going to have essentially divide k up into 50 buckets based on Y, and each bucket is going to have k divided by 50 is going to be less than, in this case, I have set an upper bound for k, which is 5,000. So in this case, this is going to be less than 100. Okay, so what is going on here? So what I'm doing here, once again, is I'm using a hash table on Y. I'm storing one representative bucket for each value of the hash table or the hash function, and as that bucket gets filled up, I write it out to disk. Okay? So as it gets filled up, I write it out to disk. Essentially, what I'm doing is a precursor to the 2-pass partition hash join for the next relation. Okay? Does that make sense? Okay, so let me try to repeat that. So alternative number 1 is I had k blocks. I could store all of it in memory. And because I could store it all of it in memory, it essentially becomes a 1-pass hash join. I store all of R join with S in memory, then I pipe through all of U, and then I'm done. Yes? So that much is clear? Okay. So let's talk about the next step. So let's imagine that I was reading in, let's say that I was not doing the join to construct R join with S, but I was just reading in R join with S. If I was reading in R join with S, if I'm doing a 2-pass partition hash join, I would be partitioning R join with S based on a hash function, which would be on Y, right? Because Y is the join attribute. Yes? So I would be partitioning it into a number of buckets. The way I would partition it is I would apply the hash function and then add it to the appropriate bucket, or the block corresponding to the appropriate bucket. Once that block gets filled up, I write it out to disk and then create a new block, and I keep going this way. Yes? Which part of that is not clear? So far all that I've done is I'm computing the results of R join with S. I'm hashing it, adding it to the hash table. I have one block corresponding to each bucket. If that block gets filled up, I write it out to disk, and I keep doing this. And essentially what I've done is I have R join with S, I have k blocks, and because I have hashed it into 50 buckets, I essentially have B of R join with S divided by 50 blocks per bucket that I've written out to disk. Okay? So essentially this is like the first step of a 2-pass partition hash join on the results of R join with S. But the nice thing is you've already computed the results of R join with S when you are working with R and S. So you don't need to read it in from scratch. You already have it there. So you might as well just partition it using the hash function. Then you write out the buckets into disk. And then the last step is just the 2-pass partition hash join step between the partitions of R join with S and partitions of U. So once again, this step allows you to do the partitioning of R join with S, and then this step allows you to do the partitioning of U. Okay, so you're basically partitioning U into 50 buckets, and finally you're reading in a bucket of R join S into memory, you're reading in the corresponding bucket of U, and then you do that join. Okay, so essentially the first step stays as is. It's 3 times B of R plus B of S. You're writing out the partitions of R join with S. So you have one corresponding to write out partitions of R join with S, and then read in so you're writing it out and reading it in, so that's why there's a 2, and then it's the 3 times B of U as because you're reading in U and you're writing out U for step 4, and then you're reading in U for step 5. Okay, so let me sort of give you these 2 steps, or actually how would I explain this better? So which part of this is not clear to you? Let me ask that question. So if I had one alternative was I compute a 2-pass hash join on R join with S, 2-pass hash, materialize the result of R join with S, and then 2-pass hash join, partition hash join on S join or R join with S join with U. So for that, the cost was 3 times B of R plus B of S. So this was the first one. Let me try to erase some of this. Okay. So rewinding a bit, the first approach was to do two pass partition hash join for this, 2-pass partition hash join for this, and then write out the intermediate result. So that was approach 1. Approach 2 was when you could store the results in memory. So 2-pass partition hash join for the first one, and then 1-pass hash join for the second, with pipelining of the intermediate results. So far so good? Okay. The third is a hybrid between the two. So I'm not going to do a complete 2-pass partition hash join. In this case, I did a complete 2-pass partition hash join for the second step. Instead of doing that, as I'm generating the results of R join with S, I'm going to do the partitioning there itself. Okay, as I'm generating R join with S, I'm going to do the partitioning at that point itself so that I don't need to do the partitioning a second time. I'm not going to write it out to disk, read it back in, and then do the partitioning. I'm just going to do the partitioning at that point itself. Okay? So what that basically says is, so in the case where I'm between 50 and 5,000, I'm going to take the results of R join with S, which I'm anyway computing, and then partition it while I've computed it. Essentially, that allows me to write out R join with S once and then read that back in. I don't need to add a 3 times or a 4 times to this, or a 3 or a 4 factor to this. It's just 2 times. Basically, it allows me to skimp on reading in or writing out one more time. So the last couple of questions here for this particular approach. So is this, so I find it hard to read your faces. So is there some part of this that's hard, or is there some part of this that's not clear? Yes?
Just to quickly clarify, because I understand what 2K is now.
Yeah.
So for the 3BR, 3BS, and 3BU, it's just like hashing it and then like reading it, like, and then writing it out and then reading it back in.
Yes.
So those are just the 3.
Yeah.
Like why it's 3 and stuff.
Yeah. So read it in, hash, write it out, read it in again. Yeah, so it's 3.
So,
yeah. And if I were to do 2-pass partition hash join, then for K, which is R join with S, I would write it out first and then pretend it's a new relation. So it would be read in, hashed out, read in, hashed, write it out, read in again. So it's 4 times for the naive 2-pass partition hash join. For this, it's as I'm generating the results, I partition it directly in memory itself, then write it out, so that's 1, and then I have to read in the partitions once again. So it's 2 times. Yeah. So if there's some part of this that's not clear, let me know. I'm going to answer these 2 questions and then move ahead. Okay, so last chance to ask me questions about this, or whichever part of this you're not clear about, because it looks like some of you may be confused, but you're not asking me any questions, so it's not clear which part you're confused by. Yes?
Can you talk about the 4K?
Okay, so the 4K one is perhaps more straightforward than this. So if you can think of the naive case to be, you do a 2-pass hash join between R and S as a step 1. Take the results of R join with S, write it out, so that's K. And then 2-pass hash join for the second step. Imagine now K or R join with S is staying in disk. You can basically work on that to give you the next factor. Okay, so I'm going to keep moving because I have one more set of slides to cover. I'll answer these two questions, come up and talk about the last alternative and then move on. So why do we partition U into 50 blocks in step 4? Well, that's because for R joined with S, so that's the K blocks, we have 50 blocks that we were storing in order to partition these K blocks, and therefore we have 50 buckets, right? So basically, R joined with S was hashed into 50 buckets. Similarly, U needs to be hashed into 50 buckets. Okay, if you're hashing on two different things, then you're not going to be able to join via two-pass partition hash join, and therefore U is also partitioned into 50 buckets in step 4 as opposed to 100 buckets or a different number. Okay, because you had only 50 blocks for storing the results of R join with S, and therefore you can have only 50 buckets. And since you want the number of buckets to match between R join with S, which is K, and U, you want U to be hashed on 50 buckets or into 50 buckets. This should be buckets, not blocks. Okay, so sorry. So this should be buckets, not blocks. It's, U is partitioned into 50 buckets. Okay. Finally, why did we have the less than 5,000 condition? Well, the way to reason about that is you have R joined with S, which is hashed into 50 buckets. Okay? So each bucket has K divided by 50 blocks. Correct? Okay. Now, in order for me to do the final join, I need to be able to store, and once again, let me wrap up the story. So for U, I have 10,000 blocks divided by 50 buckets. Therefore, each block has what, 250? Each bucket has 250 blocks. Yes? Okay. So I know for a fact that I can't store a bucket of U in memory at a time. My memory is only 101 buffers. Okay? So the only way I can do the second step of a two-pass partition hash join is to store an entire block of R join with S in memory and then cycle through the blocks of U for the same bucket. So I would need to store I would need, let's say, 99 blocks to store the bucket of R joined with S, one block for U, and one block for output. So said another way, I want K divided by 50 to be less than 100, and therefore K should be less than 5,000. Okay? So this is just because I want, for the second step of the two-pass partition hash join, when I'm joining R join with S with U, I want a bucket of R join with S to be fitting in memory at a time so that I can then cycle through the blocks of U. Okay, then the final one is if I have K is greater than 5,000, then I have no choice but to materialize the results of these. Instead of pipelining through it, I have no choice but to materialize the result and then do a vanilla two-pass partition hash join. So this was the same as before, right? So this was basically K, so 3 times B of R plus 3 times B of S, plus K plus 3 times K plus 3 times V of U. So this was the second two-pass partition hash join. This was the first two-pass partition hash join, and I'm writing out R join with S in the middle. Okay, so the overall recipe, depending on the intermediate number of tuples, is if it is less than 50, then you're essentially doing a two-pass partition hash join for the first one and a one-pass partition hash join for the second. If you are between 50 and 5000, then you're doing a 2-pass partition hash join for the first, and let's say a 1.5 partition hash join for the second. And if it's greater than 5000, then you are doing a 2-pass partition hash join, materialize, and then 2-pass partition hash join. Okay, so that's that. There's either the same example or a similar example in the textbook, so I encourage you to go take a look. This is not an easy example, okay, so this is not straightforward, so it requires you to understand both the query execution stuff pretty well as the query optimization stuff pretty well. So, so if some of this is not clear, I strongly encourage that you go back and look at these slides once again, go read the example in the textbook, and ask me if there are any questions, okay? So I'm going to move ahead and try to cover the cost or the size estimation stuff. So this is a slightly different topic. So there's not as many prerequisites to the query executions and query optimization stuff. It's like a standalone subroutine. So hopefully if you've zoned out because of the last stuff being too hard, you can be convinced to pay attention once again, okay? So this is one important ingredient that we didn't talk about in query execution and query optimization, is how do you estimate this size, right? So we had K in the previous example as a number of blocks in R join with S. How do you know what K is, right? So that's the focus of this set of slides. So you do need to know the size of a relation or an intermediate result in order to be able to estimate the cost. So, well, I think I kind of lied, but this is probably it. The cost of the partition hash join, 2-pass partition hash join, was 3 times B number of blocks of the first relation, 3 times the number of blocks of the second relation, and the number of blocks, as if the relations were clustered, were the number of tuples divided by the block size, or the number of tuples that could fit within a block. And so basically the focus of this set of slides is going to be on how do you estimate the number of tuples in an expression, okay? So let's start with a selection, okay? So you have a relation R and you're applying a selection. Let's say attribute A is being set to value C. Now let the number of distinct values of attribute A be V of R comma A. Then my claim is the number of tuples in S can be anything from 0 to T minus V of R comma A plus 1. So why these numbers? Why would it be 0? This is an easy one. So is there a case where after selection the result is 0? This is easy. Yep. Yeah, there are no values corresponding to C, right? So you say your selection is on A is equal to C, but if A does not, there's no tuple corresponding to A having value C, then T of S is going to be 0. Okay, what about the other one? This is a more interesting case. Another way to read this is any thoughts? Yep.
There's just one tuple for each of the other values of A, and the rest are all A equals C.
Exactly. So, so this comes from the fact that you know that there are V of R comma A distinct values of A, correct? So therefore there must be at least V of R comma A minus 1 tuples that have values other than A is equal to C. Okay? So you have at least V of R comma A minus 1 tuples that have a value of A that is not C. Okay, this is the smallest number of tuples that can exist that don't have value A is equal to C, and therefore if you set the remaining tuples all to have A is equal to C, this is what you're going to end up getting, right? So this is basically in the worst possible case where you have only one tuple corresponding to every other value of A that is not C. Okay, so those are the two extremes, but the way we are going to focus on this is to assume the uniform distribution across these values. So T of S is going to be T of R divided by V of R comma A, so it's uniformly distributed across the values of A. So that's it with the selections part. Let's see how to use that for estimating joins. So if I'm doing a natural join between R and S, then there are extremes once again. So one extreme is when the set of values of A are disjoint. If the set of values of A are disjoint, then the size of the join is going to be 0, right? Another interesting extreme case is when A is a key in one relation and a foreign key in another relation. Then in that case, T of R joined with S is essentially the same as T of R, because the way to think about that is you have R, for each tuple in R you point to a single tuple in S. So basically for every tuple T in T of R, in every tuple T in R, it joins with exactly 1. So the size of the join is going to be the number of tuples in R. Yes? Okay? Okay. All right. So now let's talk about more general joins. And for that we need to make two simplifying assumptions. So the first assumption that we're going to make is a value containment assumption. The assumption says that if the number of distinct values of attribute A in relation R is less than or equal to the number of distinct values of attribute A in relation S, then the set of values that A takes in R is included in the set of values that A takes in S. Okay, so this is an assumption. This is not true in general, but this is an assumption that we're going to make in order to simplify our cost estimation and size estimation. Okay, so basically this says that if the set of values of A in R is smaller than the set of values of A in S, then essentially this set of values of A in R is a subset of the set of values of A in S. Okay? So at least for the case where you have a foreign key relationship, so A is a foreign key in R and a key in S, this is true, right? So even though basically for every tuple or every value of A in R, there has to be a value of A in S that matches. And so at least for the key foreign key case, this holds, but we assume that this holds even more broadly. Okay, so then the second simplifying assumption is the preservation of value sets. So this assumption says that for any other attribute B from one of the relations R or S, when you are doing a join between R and S on A, and you have another attribute b in one of the two relations, then the number of distinct values of b in R joined with S is the same as the number of distinct values of b in R if b derived from R, or number of distinct values of b in S if b derived from S. Okay, so basically this says that if I'm not doing a join on that attribute, then that set of values is going to stay the same. Okay, if I'm not doing a join on that attribute, then that set of values is just going to stay the same. Okay, so let's talk about how this helps us estimating sizes. So let's say that you have v of r comma a is less than or equal to v of s comma a, and you're doing a join between r and s on a. Okay, so then you have, let's say, a tuple of t in R. How many tuples of S will this tuple t join with? So my claim is that on average this will be t of S divided by v of s comma a. Why is that? Yep.
To do these calculations, we put the smaller relation on the left side.
Essentially, but I'm asking a simpler question. So I'm asking the question of, let's say that the number of distinct values of R is smaller than the number of distinct values of S. Okay?
Oh, okay.
Now, for a tuple in R, how many tuples in S does it join with? Okay, and my claim is it's t of S divided by v of s comma a. And why is that? This is not super hard. So basically, I'm using the assumption that the values are contained, right? I'm using the assumption that the values are contained. So since v of r comma a is less than or equal to v of s comma a, every tuple in R is also present in S. Okay, so every tuple, sorry, not every tuple in R, but every value of A in R is also present in S. Now, given that that value of A in R, given that that value of A is present in S, how many tuples would that value of A have? Well, that's on average t of S divided by v of s comma a. Right, because we made that uniformity assumption for the selection criteria. So this is essentially sigma of S of A is equal to C, for instance, where C is basically the value of A in T, right? So sigma of A is equal to C in S is basically T of S divided by v of s comma a. Okay, so basically the way to think about this, you have a smaller relation R and a larger relation S. A given tuple T in R is going to join with a collection of tuples in S, and this collection of tuples are all of those tuples that have the same value of A as T does, and the number of such tuples is T of S divided by v of s comma a. Okay, and now T is going to contribute T of S divided by v of s comma a, and therefore overall the cost or the size is basically T of R multiplied by T of S divided by v of s comma a, because you repeat this for every single tuple in R. Yes? Okay. So in general, if you have a join between R and S on A, then the size is T of R times T of S divided by the maximum of V of R comma A and V of S comma A. Okay, because if R is a larger relation, then you're basically going to assume value containment or preservation of, I forget the names. So containment of values. containment of values in one direction versus the other direction. So if you have R being smaller than S, then each tuple in R is going to join with a certain number of tuples in S. If you have S is smaller than R, then each tuple in S is going to join with a certain number of values, a certain number of tuples in R. Okay? So here's an example. So T of R is 10,000, T of S is 20,000, V of R comma A is 100, V of S comma A is 200. The way I would do this computation is say, hey, look, I'm going to focus first on the fact that R is smaller than S. So I'm going to look at every single tuple in R and consider how many tuples it's going to join with S. So I have 10,000 such tuples in R. Each such tuple is going to join with 20,000 divided by 200. Right? 20,000 divided by 200. Actually, I made a mistake. Sorry, let me retrace a bit. So the first thing that I should do is to not compare these sizes of the relations, but compare the size of the value sets. That's what I should have done. So I looked at the number of values in R and the number of values in S, and I say, hey, the number of values in R is smaller than the number of values in A, so I'm going to loop through all of the tuples in R and consider how many tuples in S it joins with. So I'm going to loop through all of the tuples in R. I have 10,000 tuples in R. Each of those tuples is going to join with 20,000 divided by 200, which is 100. Okay? So each of these tuples in R is going to join with 100 tuples in S. And therefore, overall, I get 1 million. Okay? So once again, the way I started this was to say, look, which of these two relations has a larger V of S comma A? And then I'm going to apply containment of values to say that if V of R comma A is smaller, then this set of values that A takes is going to be contained in the set of values that A takes in S. And then I use that to compute the sizes. Okay. So when there are joins on more than one attribute, this generalizes. I won't go into the derivation, but the generalization basically says the size of the join is T of R times T of S divided by the max of V of R comma A and V of S comma A, and the max of V of R comma B and S comma B. Now, the three-way join is quite interesting. So let me work through that. So let's say I have, the interesting thing about this is that no matter what order I do the join, it's still going to give me the same value. Okay, and you can try to confirm this to yourself as well. So let's try to do R join with S and then join with U. Okay, so it's R join with S, then join with U. Okay, and I'm trying to come up with the size of this. Okay, so let's first try R join with S. So in order to compute R join with S, first I notice that R and S have attribute B in common, and I also notice that the number of values that B takes in R is greater than the number of values that B takes in S. So the way I would do this is to first look at the number of tuples in S, so that's 20,000. And then I'm going to say that these 20,000 tuples, each of them is going to join with 10,000 of R divided by 100. Okay? So this is the first step. This is the size of R join with S. Then I want to compute the size of R join with S join with U. Now, when I take R join with S and U, the attribute that is in common is C. Okay, so the join is going to happen on C. Now let's look at the number of values that C takes. So for S, the number of values, and before I get to R joined with S, since the preservation of value sets says that assumption says that V of R joined with S, comma C is going to be V of S, comma C is going to be 40. Okay, so when I'm not doing a join on an attribute, then that set of values is going to stay the same. Okay, so why do I need that? Well, I need it to compute the results of the join between R join with S and U. So R join with S and U, both of them have attribute C. V of R comma S comma C is 40. V of U comma C is 20. So basically, every tuple in U is going to join with a certain number of tuples in R join with S. So I will loop through the tuples in U. So I have 10,000 tuples in U, right? And the number of tuples in R join with S that each tuple in U will join with is 20,000 times 10,000 divided by 100. That was just the size of R join with S divided by V of R join with S comma C, and this is equal to 40. Okay, so overall I have 10,000 times 20,000 times 10,000 divided by 100 times 40. Okay? So this was one way of computing this. I can try another one and see whether that gives us a different cost. So let's try S join with, let's see. Okay, let's try a very different one. Let's try R join with R cross product with U, or R join with U but there's no attributes in common, join with S. Okay? Here the cost of R join with, or the size of R join with U is basically going to be, the tuples are going to be multiplied, right? There is no attributes in common, and therefore it's just going to be 10,000 times 10,000. Okay? Now between these two, you have two attributes in common. You have B in common and you have C in common. And going back to this slide, if you have more than one attribute in common, then you just divide by the max of the number of distinct values for the first attribute and the max of the number of distinct values for the second attribute. So this was the T of R comma U, R joined with U. Let me rewrite this. Okay? Okay, now this I said the number of tuples in R joined with U is nothing but the product of the two, because it's essentially a cross product. So you have 10,000 times 10,000. T of S is 20,000. Now what's the number of distinct values of B in R joined with U? So for R joined with U, using the preservation of value sets, the number of distinct values of B is going to be the same as the number of distinct values of B in R. So that's going to be 100. And the number of distinct values of B in S is 50. Then the number of distinct values of C in R joined with U is drawn from the number of distinct values of U, of C in U. So that's max of 20, 40. Right? So once again, you have this evaluating to 100 and this evaluating to 40, which was the same expression as we had the last time around. Okay, so basically the nice thing about this is that using these two assumptions, the containment of values and preservation of value sets, you end up, no matter which order of joins you use, you end up with the same value, which is nice, which is what we want. Okay, so so this was the expression that we had. I think this should be 10,000. Okay. All right, so that's it. Do we have any questions on this part? Okay, all right. So there's no class on Wednesday. I'm out of town for a conference. Classes will resume on Monday. Okay, so that'll be our last week of classes. All right, see you on Monday.
The finals the Monday after that?
I think so. Yeah.
And then do we have class the Wednesday after that, the last day of classes?
No classes after the final.